course. So far we have outlined what we do in this course, what we plan to do in this course on Galois theory, and I told you that in the initial videos I will recall some of the basic concepts of group theory, ring theory, field theory that we will need. So in the last video I recalled facts about group theory that we require. So today I am going to start recalling what we need to know about rings and fields. And as I commented last time, these are obviously not going to be exhaustive revisions. I am only going to quickly tell you the key and important results and properties of these rings and fields that we require constantly, that we require and use in this course on Galois theory. Okay, so if you recall, group I recalled for you last time is a non-empty set with one operation. Rings are non-empty sets, very briefly, non-empty sets with two operations. Okay, so we usually denote them by plus and into, addition we call them, and multiplication. And if R is the set which has two operations, it is an abelian group under the addition operation, one of them. So that's one of the requirements. And so in other words, it has an additive identity which we call 0, and you have multiplication is not necessarily a group operation. Okay, so and into has some of the properties, the multiplication has some of the properties, has a multiplicative identity, has an identity denoted by 1. 0 is always the additive identity. It is associative and it is commutative. So these are the assumptions we will make. Okay, this is our setup. Okay, so that there is a multiplicative identity is our assumption. Similarly, that multiplication is commutative is an assumption that we make. You can also consider rings where these are not true, and that's a separate theory, but associativity is always required. What we do not require is inverses. Okay, so the typical examples are the most important examples for us. Okay, so before I write the examples, also I'll mention what is a field. A ring is a field. Fields are special types of rings. If R minus 0 is a group under a multiplication. Okay, so certainly you cannot put 0 and expect that there is a group operation, because 0 cannot be multiplied with anything to get the identity element 1. So 0 cannot have an inverse. But if every non-zero element has an inverse, we talk of, we'll say that it's a field. Okay, so the main examples. So this is not a course on ring theory and field theory where you study these in general, but in Galois theory the main examples that we will mostly be looking at are Z, of course, is the ring of integers. This is the first ring that we study, and this is not a field because multiplication doesn't have inverses, right? 2 doesn't have an inverse, whereas Q, R, C are fields. So they are rings and they are also fields. Also we can consider Z mod PZ, or in general Z mod NZ. So these are classes of rings that I am writing. Z mod NZ is a ring for every positive integer. This is an important ring for us. Okay, integers modulo n. So you can go modulo an ideal, and that gives you a quotient ring. So again, I am not discussing those in detail. And we know that Z mod NZ is in fact a field if and only if n is prime. Okay, so that's another fact about. In fact, here I can also admit 0. So I'll say non-negative integer. When you take n equal to 0, you get the integers itself, Z itself. So this is another important class of fields for us. So we usually denote Fp to be Z mod Pz Pa prime. So these are special kinds of fields. These are called finite fields because they have only finitely many elements. Okay, and another important class of rings for us is the polynomial rings. So if R is a ring and x1 through xn are variables, so these are indeterminates. Okay, they have no meaning, they are just symbols. You can consider polynomial ring in n variables over the ring R. So typical elements are things like this. So maybe a1 x1 square plus a2 x1 cubed x3 a4 a3. I'm just randomly writing something. So things like this. So often we will be interested in polynomial rings in one variable. One variable rings are, one variable means, this means n equal to 1. This is often the most important case for us in this course, but we can also look at other examples, 2 variables and so on. So case for us. In this course, the most important example is n equal to 1. So that means we look at, for example, polynomial rings in one variable over rational number. So here it will be things like this. Okay, so this belongs to this. So if I have only one variable, I typically denote that by x. Okay, so these are some of the important examples of rings in this course. And recall also the notion of ideals. Okay, I have not defined this, but ideal in a ring is a subset of a ring which is a subgroup under addition and it is closed under multiplication by any ring element. So again, the typical examples I will give, so you will recall the definitions in case you forgot, you recall them after this class, but typical examples are nz in z. So this is all integers of the form a in z. Okay, so these are multiples of n. In zx, x is an ideal, right? So x is an ideal. It is defined to be all polynomials where the constant term is 0. Okay, so it must be, so remember the definition of is that it is x times some ring element. G is arbitrary, right? So which is to say that every polynomial whose constant term is 0 must be a multiple of x, obviously, because if you take, let's say, 2x square minus 3x plus 2, this is not in x because you cannot multiply this with x, whereas 3x cubed minus 6x square plus 7x is in x. Okay, because this is simply x times 3x square minus 6x plus 7. Okay, again I am not giving you full definitions or precise definitions, but just giving you a flavor of what ideals are. Ideals are very important in ring theory. Just like subgroups are important in group theory, ideals are important in ring theory. And we have special classes of ideals called prime ideals and maximal ideals. So quickly recall, what is a prime ideal? So I in R is a prime ideal, or we say it is prime if, of course, it is an ideal in addition to being an ideal, and it has the property that if AB is in I implies A and B are in R, and AB in I implies that A in I or B in I. Okay, so equivalently we say that R mod I is an integral domain. These are important notions and terminologies which you should recall before we go further in this course. Okay, integral domain means no non-zero divisors. That means if you multiply two non-zero elements, you get a non-zero element. So examples, the ideal we considered earlier is a prime ideal, whereas x square in the same ring is not a prime ideal. Okay, because x times x is there in this ideal J, so x times x, which is x square, is in J, but x is not in J. You cannot write x as a multiple of x squared, right? Because if you multiply by x squared, the degree is at least 2. So x itself cannot be in the ideal, so it is not a prime ideal. The other important class of ideals is called maximal ideals, and as the name suggests, these are ideals which are maximal. So I in R is maximal. Of course, if it is an ideal, I will write it to emphasize that. And if I is contained in ideal J which is contained in R, this is an ideal, then either J is equal to I or J equal to R. So you cannot have an ideal, proper ideal, that's strictly bigger than I. Okay, so those are maximal ideals. So in the class of proper ideals, they are maximal elements. So this is a maximal ideal. Example, the prime ideal earlier that we considered, you can think about it and conclude that it is in fact not a maximal ideal. Okay, why is that? This is clear because if you take ideal generated by x comma 2, it's not equal here and it's not equal here. Okay, so this is contained in a bigger ideal which is a proper ideal also. So this is not a maximal ideal. So in fact, you can check that x2, x comma 2 is a maximal ideal of Zx. You can't construct a proper ideal which strictly contains the ideal x comma 2. So also this is a useful criterion. See, an ideal is maximal if and only if R mod I is a field. Okay, so you can see that Zx modulo x is isomorphic to Z, not a field, right, which confirms the fact that x is not a maximal ideal. On the other hand, if you go Zx modulo x comma 2, this is in fact isomorphic to Z mod 2Z, because you kill x, so then you remain with Z, and then you kill 2 in Z, so that will give you Z mod 2Z. So this is a field, so that means this is not maximal and this is maximal, right? So that tells me that you have these are important notions, prime ideals and maximal ideals. Okay, so one thing that I should probably just clarify or maybe recall for future use, if you have a ring R and you have elements A1 through An in R, the ideal generated by them is denoted by A1 through AR in brackets. Okay, and this is simply you take all ring elements Bi's and take this. Bi are arbitrary ring elements. Okay, so you can check that this is an ideal, which is a very easy check. Okay, so this is the ideal generated by a single element, by R elements. Now if you take one element, you get what is called, so this is R, N. Okay, principal ideals are ideals generated by one element. So again, example, x is a principal ideal of Zx. Okay, but x comma 2 is not. Okay, this requires some thinking, because the point is, even though I have defined this to be generated by two elements, it's conceivable that there is some other element which generates this. For example, x can also be written as x comma x square. I mean, I can always give 2, but I don't need the second one. So here you have to argue this. You have to argue that there is no single element which generates this. So this is a good exercise to recall and refresh your ideas about rings and ideals. Okay, so these are the notions of principal ideals, prime ideals, and maximal ideals. Just to continue this, so a few more theory things about ring theory. So now let's focus on polynomial rings, because this is going to be at the heart of this course. So I'm going to use several things about polynomial rings constantly in this course. So let's recall some important results about polynomial rings. So let's stick to a general case as much as possible. R is a ring, and let's consider in fact polynomial rings in one variable. So Rx. So if fx is in Rx, the general description of fx is like this: an xn, an minus 1 xn minus 1, a1x plus a0, and recall that it is a ring, it is a polynomial over R, which is to say that ai's are all in R. Okay, so the degree of fx is called n if an is non-zero, right? You can always add zeros in the beginning, which we don't want to do. So if an is non-zero, it is called, the degree is called n, and the leading term of fx is an xn, so the highest degree term, and the leading coefficient of f is en. Okay, so the leading term is the entire first term, and the leading coefficient is just the coefficients of the leading term. So ai's are called the coefficients. And the constant term is a0. So that means is the degree 0 term. So that is constant term, and that, as I noticed earlier, it is actually just f0. When you plug in 0, all the x terms will go away and only the constant term remains. Okay, so now what is a root of such a polynomial? A root of fx is an element a in R such that fa is 0. Okay, so the roots may not live in the ring R itself. Maybe there is a bigger ring which contains the roots. So this a root should be thought of as some element in an extension ring of R. But for now, let's say a root is an element a in R such that fa is 0. For example, one thing you can say is that fx is in the ideal generated by x if and only if 0 is a root of f. Right? So 0 is a root of f if and only if you have the ideal is in the element polynomial fx is in the ideal generated by x itself. So now remark is that roots may exist in bigger rings. Okay, so this is somewhat vague. What do you mean by bigger ring? Is an extension ring. So again, example, so x square plus 1 has no root in R. It is a polynomial over R, but it has no root in R, but it has a root in C, right? For example, the imaginary number I is a root of this. Similarly, x square minus 2 has no root in the rational numbers, but it has a root in R, right? But in fact, it also has a root in much smaller ring than R. For example, you can take q adjoined root 2. So in my review of field theory, I will describe this late in detail, but suffice for now to say that this is a field. Okay, so it doesn't have a root in q because square root 2 is not rational. However, taking a slightly bigger field, you get a root. On the other hand, 2x minus 1 has no root in z, but it has a root in q, right? 1 by 2 is its root, but it's not a real, it's not an integer, so it has no root in z, but it has a root in rational numbers. Okay, so this is sort of important phenomenon for us. The course will analyze this situation where you have a given polynomial over a given ring. The ring itself will not contain roots, but you can construct roots in a bigger ring. So important phenomenon, I'll write it like this for now. So this is an important phenomenon for us in this course. Okay, so now continuing this, a polynomial is irreducible, polynomial fx. So I told you that Rx, the polynomial ring, is a ring, so you know how to multiply two polynomials. So addition is also easy, you just add like terms degree wise, but multiplication is a bit more tricky, but you all know what multiplication of polynomials in Rx is. So we call this irreducible. A polynomial is irreducible if it cannot be factored as fx equals gx times hx, where okay, so I will give you the easy definition here, where degree gx and degree hx is less than. So of course you can always write the polynomial as 1 times itself, so that is not allowed because the degree doesn't drop. So you cannot factor it into product of two polynomials which both have smaller degrees. Okay, for example, x square, and I want you to emphasize here irreducible. Here I should write in Rx, because irreducibility is a property of the ring which you are working with. So irreducible in Rx if it cannot be factored as this, where g and h are in, of course, Rx. Okay, so if you take x square minus 1 in qx is reducible. So if something is not irreducible, we call it reducible, since you can factor this as x minus 1, x plus 1. Okay, so this you can see is degree 2, this is degree 1, and this is degree 1. So this is f, you have written it as g times h, where g and h have both degrees 1, which is less than degree of f, which is 2. Okay. On the other hand, x square plus 1 in Rx is irreducible, since we can't factor. So this you have to convince yourself, because if you could factor, degree of x square plus 1 is 2. So if you can factor it in a valid way, it has to be degree 1 and degree 1, right? Because also remember, when you write like this, degree of f must be degree of h plus degree of g, right? And both are non-zero, both are, yeah, so that's another way of saying this. Because if one of them is 0, the other is equal to degree of f. I am asking both of them to be strictly less than degree of f. That means both are non-zero. So these are all non-negative numbers. So if you factor this as product of two polynomials, h and g, that means degree h is 1 and degree g is also 1, because it has to be strictly less than 2. But that means h must be of the form, because this is a monic, you can always write like this. Where a, b are real numbers, right? So you can write it like this. But then this is the important observation. So this is important. A and b are roots of x square plus 1, because if you do call this f, so f of a is h of a times g of a, that is 0 because h of a is 0. But of course you know x squared plus 1 has no roots. Okay, so I have essentially proved that it is irreducible because it doesn't have roots. On the other hand, x square plus 1 is reducible over R, or C, sorry, because x square plus 1 can factor as x plus I times x minus I. Okay, so you do have factorization in Cx and not over Rx. So we say the terminology is that we say that x square plus 1 is reducible over Z Q R, okay, because the same logic that I gave here, that it doesn't have roots in R, obviously implies that it doesn't have roots in Q as well as in R, in Z. So it is irreducible over that, but it is reducible over C. Okay, so this is the terminology that we want to follow. Okay, so now we can talk about irreducible factorization of polynomials. Okay, again I don't want to get into technicalities here. Quickly, I just want to essentially give you an idea of what happens. It is simply an irreducible factorization of a given polynomial is simply a product as irreducible polynomial. So each fi is irreducible. Okay, so for example, x squared plus 1 in Cx has irreducible factorization, x square plus 1 equals x plus I times x minus I.
I found this on the web for tuition.
Okay, so this is the irreducible factorization. But in Rx, it is already irreducible. So x square plus 1 is x square plus 1. This is the irreducible factorization. And here it is the irreducible factorization. Okay, so this is irreducible factorizations. Okay, and then there are some technicalities involved, what is allowed, what is not allowed, and whether they are unique and or I don't want to get into all those details.
Okay,
so
I found this on the
UFDs are irreducible rings where there is a unique, so okay, so I don't want to again define UFDs for in full generality are rings where I will not define it in full technical details, but quickly the definition of UFD is that rings where every element has a unique factorization into irreducibles. Okay, so the main theorem that we will recall at this point is, if R is a UFD, then Rx is a UFD. Okay, so this is covered in many courses on ring theory. The main examples of this are, so Z is a UFD. Okay, so Z is a UFD is a statement that you you learn in school essentially. So this is the fundamental theorem of arithmetic. Okay, so every integer can be written as a product of prime numbers in a unique way. Okay, so zx is a UFD. In fact, because zx is a UFD, you can take two variables, three variables. Two variable polynomial ring is a one variable polynomial ring over a one variable polynomial ring. So continuing like this inductively, you conclude that this is a UFD. Similarly, a field K is a UFD. So implies Kx is a UFD. Okay, this is in fact the most important statement for us. Polynomial ring in one variable or a field is a UFD is a very important fact for us. Some other examples of UFDs, or rather non-UFDs. So this is a non-example. So if you take z adjoined square root minus 5 is not a UFD. Okay, this is covered in my ring theory course, for example, or you can look up any book in ring theory. Here it turns out that the element 6 has two factorizations. So these are distinct factorizations. Okay, so again, this will rarely come up for us in this course, or in fact never. It will probably never come up, but I just wanted to give you an example of a ring which is not a UFD. Another important class for us is called PIDs. So this is a short form for UFD is a short form for unique factorization domains. Okay, so factorization is unique and they are domains, so they are integral domains. So PIDs are principal, ideal, PI domains. So these are rings. R is a PID if every ideal is principal. Okay, these are very special classes of rings, and the main example for us, or main examples, let's say Z, and this is again Euclidean division. You take an ideal in Z, it must be generated by the least positive integer in that ideal. Similarly, Kx, where K is a field. A field is automatically a PID because field has only two ideals, the unit ideal and the zero ideal. But the more important example is polynomial rings in one variable or a field are PIDs. And the key idea here is use Euclidean division, both in the case of integers and polynomial rings over a field in one variable are PIDs, because in the case of integers you take the least positive number in that ideal. In the case of polynomial rings in one variable or a field, you take the polynomial with the least degree in that ideal, and then you apply division algorithm, conclude that those elements generate those ideals. Non-examples: Zx and K x1 through xn, where n is greater than or equal to 2, are not PIDs. Okay. These are UFDs. They are very nice UFDs, nice rings, namely they are UFDs, but they are not PIDs. So an easy fact you can check, this is again covered in an algebra course, is that if something is a PID, implies it is a UFD. Converse not true, as these examples show. Right, Zx and K x1 through xn, where n is at least 2, are UFDs, but they are not PIDs. Okay. So let me stop this video. So in this video we recalled ring theory, some important theorems in ring theory. We talked about prime ideals, maximum ideals in a ring. We talked about factoring polynomials. We talked about what roots of polynomials are. We learned we recalled what are UFDs and PIDs, and I told you that UFDs are very common and almost all the rings that we study are UFDs, whereas PIDs are less common, but in fact though the main interesting rings that we study in this course are PIDs. Okay, so in the next video I'm going to recall another important notion in ring theory called irreducibility criterion. So these are important things for us because later on in the Galois theory course we are going to need to determine whether a given polynomial is irreducible or not. So in this video I'll stop now, but I'll start the next video by recalling some of the important techniques for determining if a polynomial is irreducible or not. Thank you.